We are going to start talking about a new topic, which is electric potential. As we get started with this, I want to briefly remind you of our terminology because this is a place where if you start thinking that some of these different topics are the same, you're really going to get stuck. So first, remember that we started a while ago talking about electric field. An electric field was coming from the idea of force, where force is something we can directly observe. Then, in the previous sequence of videos, we talked about potential energy. And potential energy was something familiar from mechanics. It's an energy stored in a configuration of a system. And while we can't necessarily observe the energy directly, we can infer about energy based on how we see energy transformed. So for instance, we can see energy of potential becoming kinetic energy. And we see that velocity very clearly then. The new topic is going to be electric potential. Notice that the word potential is showing up in two places, both in potential energy and now in electric potential. If I use just potential by itself, that actually means this case, electric potential. In general, I'm going to try to be careful to say electric potential, especially in these videos, since I know that this can be confusing. However, myself and others, like in the book, will just refer to potential when we mean this. Something else you might see is this, for different reasons, might be called voltage. We're also going to be talking about potential difference, which relates to this. So please just be careful as we are introducing something new that sounds a lot like something we already saw. So what is electric potential? We're going to think of this somewhat like electric field. So for electric field, we said that there's a force that is not directly due to two objects touching one another. So we can think about a source causing the field that then causes the force. Here, we're doing the same thing, but it's with potential energy. So electric potential is this V, and that's going to be the potential energy divided by the charge you're specifically thinking about. Or you can rearrange this to say that the potential energy of a specific point charge and all of the sources that it's near is going to just be equal to the Q times that charge times the potential at the point it's located at. So this is a way of talking about potential energy, but without talking about every single charge that might be occurring. We can break this into the source, which creates V, the electric potential, and then again our probe charge or our source charge, just like we talked about with electric field and force. So that's kind of a parallel that's happening here. So whenever you're talking about electric potential, be really careful in that potential is caused by the source charges, and if you want to get potential energy, you then multiply it by a Q that is not part of your source. The units is going to be the volt, and one thing that is very confusing is that we use V as the variable, we also use V as the unit. So in the book, one is italicized, one is not. I'm not always going to be good at distinguishing that in my slides, and you're definitely not going to be good at distinguishing that in your writing. So be really careful about this, that capital V can be a unit or it can be the variable. So this is one reason why when you're doing out your work, either everything should be in terms of numbers and units, or everything should be in terms of variables. Then it's really clear what V you're referring to. The volt can be broken into a joule per coulomb, and that's just coming from this, that U for potential energy has units of joules, and Q, our charge, has units of coulombs. So it's just a joule divided by a coulomb. And obviously a joule gets broken into other SI units as well, if you wanted. So this is the idea of the electric potential. We're now going to go ahead and look at a variety of scenarios, situations that we're going to use it in. And I just want to stress that actually electric potential is something we're going to be talking about much more than potential energy itself. So we're getting to this idea from potential energy, but electric potential is actually more useful. So again, let's distinguish carefully what it is now that we've actually met it in a little more detail. So electric potential as a property of the source charges. And again, the source charges are different than the charge that you're actually placing somewhere in space and thinking about what happens to it. And that's just like the electric field. When we met the electric field, we said that that's also a property of the source charges. So really soon, we're going to be talking about the relationship between electric field and electric potential. If there is a charged particle there or not to experience doesn't matter. So again, if we have all of space, look at that awesome drawing. We have electric potential defined everywhere. Again, it might be zero, and this is one way in which it is very similar to the electric field. It is defined for every point in space. Again, this is not electric field. This is a different quantity. It's also a scalar. Note that we haven't yet talked about directionality. So electric potential is not a vector, it's a scalar. Potential energy is going to be the interaction energy of the charged particle, a charged particle, so you can think of this as your probe or your test, which is the terminology we used for the force in the electric field, and the source charges. So in this case, we have something specific that's interacting and what it's interacting with. Here, we don't actually need that specific thing. And obviously, the units are different, so please be careful. So last, we can start to think about the potential energy and, electric potential and motion. And again, we talked about motion with electric potential, so this is similar, it's obviously related, but we can directly use electric potential rather than using potential energy. If we have a positively charged particle, it is traveling initially, note that its initial velocity is here. If it's initially traveling in the direction of higher potential, it's going to slow down, right? So this is basically saying it's going uphill. If, on the other hand, it's traveling towards lower potential, then it is traveling downhill and it speeds up. So we can directly use potential to infer whether a charged particle is speeding up or slowing down. And again, this is going to be something that depends a little bit on the sign. So this is true for positive charges, but it's going to actually be the opposite for negative charges. So here, if we have increasing, which means that, remember that this is just your final potential minus your initial potential whenever we write that delta here. So if it is traveling towards increasing electric potential, a positive charge slows down and a negative charge speeds up. This is going to make a little more sense when we tie this back to electric field. So you're going to be able to see that this is still self-consistent with what we said about fields and forces. If it's decreasing, so effectively we're kind of going downhill in terms of potential, a positive charge would be speeding up, but a negative charge would be slowing down. So do note that these flip when you're talking about positive and negative. So one way that I think about this, if you find this a little challenging, just learn this top one, right? Think about how a positive charge interacts with potential. And then if you have a negative charge, remember that you have to flip everything. So that's one way to try to simplify this.